Hello, good morning, Calculus 2. I'm still working on the disk method in section 7.2. A couple more advanced problems here. I like this one. It says prove the volume of a sphere is, the volume is 4/3 pi r cubed. So a sphere of radius r has a volume of 4/3 pi r cubed. Maybe you know that formula, maybe you've heard that formula. We want to prove it using the disk method. So the disk method can find the volume of a solid of revolution, but what we need is, but we need a 2D shape to generate that solid. So to get a sphere, what sort of 2D shape would you use? Probably a circle. A circle spun around the x-axis, or maybe would be a sphere. Maybe not even an entire circle. Maybe all I really need, I think, is a semicircle. And if I'm going to prove this for a radius r, then I need to kind of do this in general for any radius r. Sometimes those are a little tricky for students. Sometimes what you could do is practice doing it for a radius 3. And then you could see sort of how to do it, and then go back and fill in just a general radius r, treating r like a constant. I'll just do it with a radius r. So if it's a radius r, semicircle, the radius goes, that x value is negative r, that x value is r, that y value is r. And the equation of a circle, it helps to know a little bit from pre-calculus, the equation of a circle centered at the origin. That was smart of me to center it at the origin. Why center it off center? Is pretty easy. It's x squared plus y squared equals r squared. Again, let's treat r like a constant. It's some fixed radius r. Okay, that's the equation of a circle. If I'm going to do the disk method, I remember how to do the disk method. I got to do an integral. Pi is out front. And as it spins around the x-axis, I think this will work. As it spins around the x-axis, I'll create a sphere of radius r. All I need is the radius of my disk. I have a disk of volume, and it's got a thickness of dx, and I need the radius of that disk. The radius is the function. That's what we've been learning in a lot of these problems. The radius is that y value, that function. Oh, it's the y value, so I should solve for y. If I solve for y, I move the x squared over and I take the square root and I get plus or minus the square root of r squared minus x squared. So that was my circle, and this is also my circle solved for y. I really just want that semicircle, and that upper semicircle is the positive square root, so I could ignore the negative. The negative square root is the bottom semicircle. So that positive square root is the upper semicircle. That's the equation. That's my y. That's the radius of my disk. So that's square root of r squared minus x squared squared with respect to x. Pi r squared with respect to x. Yeah, oh, I need some bounds for this integral. These little disks are going to move from negative r to r. Unless you wanted to change the problem last minute, like I tend to do sometimes. I could go from negative r to r. We could do that problem. Or I could go from 0 to r and double it. 0 to r and double it using symmetry. In other words, now I'm doing a quarter of a circle, spinning it around, getting a hemisphere, and then doubling it to get the whole sphere. I think I'll do that. I'm going to go from 0 to r and double it. All right, and then you can do this. It's easy. Remember, r is a constant, treating this little r like a constant. Here we go. Let's see, first step would be to, square it. When you square it, you get r squared minus x squared. You cancel the square root. All right, well, this is easy to integrate. When you integrated r squared with respect to the variable x, you get r squared times x. When you integrate x squared with respect to x, you get 1/3 x cubed. All right, out in front is a 2 pi, and we're going to evaluate from 0 to r. When I plug in my r, I get an r cubed Right, plugging in r for x, plugging in an r there, minus a 1/3 r cubed. And this, here comes plugging in the 0, and plugging in the 0 subtracts a couple of zeros. That was the advantage of using that 0 bound and doubling it. There we go, there's a 1r cubed minus 1/3, that's 2/3 r cubed. Multiplied by 2, that's 4/3 pi r cubed. That's 2/3 r cubed multiplied by 2, that's awesome. That is awesome. I'm going to do another problem. I'm going to say, what if we had a sphere? Sorry. I want to do this problem. What if we had a sphere? And let's just say it had a radius of 3. And I wanted to remove 1/3 of the volume. I want to remove 1/3 of the volume by drilling a hole through the sphere. So I want to drill a hole through here and remove 1/3 of the volume. This is a good problem. The question is, what is the radius, or what is the radius of this hole we're going to drill through here? So I've got this unknown radius. I'm going to call it A, is the radius of this hole. And I'm going to drill out a hole of radius A, and the question is, what's A? To remove 1/3 of the volume from a sphere of radius 3. Well, let's see. Maybe we want to know what is the entire volume of the sphere first. I'm going to get rid of this last problem, I'm sorry. Erasing the last problem. But we do know this formula, and we just proved this formula. So what is the, if it is a radius, we have a sphere of radius 3 here. So I made up a problem, and I didn't write it all out for you too well. Sphere of radius 3, find the radius A of a hole that you're going to drill through there that will remove 1/3 of the volume. Well, what is the volume? 4/3 pi r cubed with a radius 3. This is the volume. That's, oh, that's 36 pi. So the volume is 36 pi. So I want to remove 1/3 of the volume. So I want to remove 1/3 of that. What's 1/3 of that? 12 pi? So I'm going to remove, let's be careful how we talk here. I'm going to remove 12 pi worth of volume. How much is left? That leaves us with 2/3. That leaves us with 24 pi. So that's the volume I want left over. So it depends on how I set this problem up. I can set it up to calculate the removing volume, or I can calculate the remaining volume. I think I want to calculate that white area, which is the 24 pi, the 2/3 of the volume that remains. So let's set up a better picture here, over here. So I've got a circle, a sphere, or I've got a semicircle of radius 3. What is the equation? Well, the equation of a circle is x squared plus y squared equals 9 when it's radius 3. When you solve for y, you get that square root of 9 minus x squared. You move the x squared over, you take the square root, so that's the upper semicircle. You have a line coming through here called y equals a. Remember, it's got this height a, and so it's a horizontal line called y equals a. And we're going to try to find that a. Now we're going to set up an integral to get this volume as you spin it around the x-axis. Wow. As you spin this around the x-axis, let me ask you a question. Is there a hole in it? Yeah, there's a hole in it. That's the hole we're trying to drill out. Okay, that's going to create an integral. It's going to be a pi out front. I'm doing the dis method. But the dis method with a hole in it means I have an outer radius. What is this outer radius? Oh, that's the function. That's the semicircle. That's the outer radius squared minus the inner radius squared. The inner radius squared is that radius, which is that height A. Good, that's the problem. I'm removing a hole, and guess what that volume is? I know what that volume is. That volume is 24 pi. It's that volume of what's left over if I remove a third. This volume is 24 pi. Now again, I left out one thing on this, very important thing. That's an A, that's a 9, watch out. I need bounds. I need some bounds here. Now, what am I gonna do? Again, let's just go, I can go from here to here to get that volume. Now that's not 3, you guys, that is not 3. That is wherever A intersects the semicircle 9 minus x squared. Aha, I need to find that point of intersection. Wow. What if you squared both sides? A squared equals 9 minus x squared. What if you add the x squared over here and subtract the a squared here? X squared would equal 9 minus a squared. Watch your 9s and your a's, sorry about that. Take the square root, there's x. X is the square root of 9 minus a squared. That's that bound. That's that x value, where A meets the semicircle. There it is. Wow. So what could I do? Again, I'm trying to get that whole volume. I guess I could I go from 0 to the square root of 9 minus a squared? That's my bound for x. And double it. Since I went from 0, I'm going to double it. All right, I've got this set up. Wow, dude, this is a pretty heavy-duty problem. You want to solve for x. You want to solve for A to find that radius that removes 1/3 of the volume. Find the radius that removes 1/3 of the volume. Wow. All right, I should just leave you with that. Or maybe I should help you do it. We've done some problems like this. I think we did a problem like this with area, where you had to solve for A. All right, I'm going to get rid of this so I got a little room to work. And I'll help you do this. Let's see, I'm trying to solve this equation. Hey, do you mind if I divide by 2 pi and divide by 2 pi? That'll leave me a 12 over here equals the answer to this integral, which is the square root of, the integral from 0 to the square root of 9 minus a squared. And then I'm going to integrate this. Now hang on, what is this? When I square that, it's a 9 minus x squared minus an a squared. And I'm integrating with respect to x. So here we go. Let's integrate with respect to x. 9x minus 1/3 x cubed minus a squared times x. Remember, a is some constant. A squared is some constant. We integrate with respect to x. We evaluate from 0 to this nasty square root of 9 minus a squared, and it's going to equal 12. But I plug this in for x. I plug the 0 in for x next. That'll be a bunch of zeros. So I really just plug this in. Here we go. This turns into a hell of an algebra problem. I got this square root of 9 minus a squared minus 1/3 times this square root of 9 minus a squared cubed minus a squared times this square root of 9 minus a squared. Man, I'm doing good. We're doing good. The only mistake I made, I should have used a 9 with an a squared. I should have used a different radius. That's okay. This is fun. Hey, I want to, I got to solve this algebraic equation. And I guess I've done some problems like this before. The smart thing would be factor out a square root of 9 minus a squared. There's a square root of 9 minus a squared there. There's 3 of them there. And there's 1 of them there. Let's factor out a square root of 9 minus a squared. And it leaves me with, when you factor a square root out of this, and there's a 9 there. Hey, when you factor it out of this, there's 2 of them. You factored 1 out, there's 2 of them. It's squared. You're squaring a square root. You get 1/3 times 9 minus a squared without a square root. You factored it out of there, you're left with a squared. Cleaning this up, you have a 9 minus a 3 plus a 1/3 a squared minus an a squared. I distributed that negative 1/3 correctly. That's a 6 minus 2/3 a squared. If you factor out the 2/3, factor out a 2/3, I think you're left with 9 minus a squared. That is correct. This square root is sitting out front. If I distributed that 2/3, I'd get the 6 and I'd get that. I factored a 2/3 out of that. Wow. This is still equals 12. All right, I'm getting close, you guys. I'm sorry. This is an advanced problem. We're about to solve this, though. I'm going to erase this stuff. I got to move back over here, moving back over here. Hey, can I take this 2/3, move it over here? In other words, divide by 2/3 or multiply by 3/2. Multiply by 3/2, that turns into 18. And then this is a square root of 9 minus a squared. This is a 9 minus a squared to the first. Together, that is a 9 minus a squared to the 3/2 power. I brought the 2/3 over. I joined that together. All right, well, in order to solve for a, you need to raise both sides to the 2/3. Raise this to the 2/3. Raise this to the 2/3. And we get 18 to the 2/3, which I'm not going to do. And this cancels. We get 9 minus a squared. Man, we're close. To solve for a, let's add it to this side. Let's subtract this to this side. A squared is 9 minus 18 to the 2/3. And finally, take the square root of both sides. A is the positive square root of 9 minus 18 to the 2/3. Wow, that's the number you need to drill a hole and remove 1/3 of the volume. Jesus, what the hell is that number? What is that number? I'm going to pick up a calculator and try to find that number. 9 minus 18 raised to the 2/3. Did do that right. That's about a 2.13, and then I need the square root of that. So when I take the square root of that, it's about a 1.4600. So I'm rounding it off here. About 1.46 removes 1/3 of the volume from a sphere of radius 3. That's interesting. All right, thanks for listening.